the contraction mapping theorem and its applications. So before we move on to the applications, let us see what is a contraction map and the theorem. Let us take the metric space x comma d. Now t from x comma d to x comma d is a map. Then t is said to be a contraction map if there exists a constant c such that the distance between t of p, t of q is less than or equal to c times distance between p and q. For c lying between 0 and 1, and c can take the value 0 for all p, q and x. Let us take an example. Defining t in the real and Newton metric, we realize that t equal x by 2 satisfies the above condition, whereas t equal 3x does not. We also know that every contraction map is uniformly continuous. So what is the theorem? Let x comma d be a complete metric space. If t from x comma d to x comma d is a contraction map on x, then t has a unique fixed point in x such that t of p star equal to p star. T being a contraction map, we can have at most one fixed point. And furthermore, we have seen that p star is the limit of the sequence, where each term of the sequence is the image of its predecessor, starting from any arbitrary term of the metric space. Thereby, we see that limit ending to infinity t power n of p equal to p star. This last point is extremely important in knowing the Newton-Raphson method. So what is the Newton-Raphson method? Let us see a short video.
Notice that this function f of x has 5 roots. Now, in this Newton-Raphson method, we do not need to actually know the root before we start. Let us assume any arbitrary point x1, locating the corresponding coordinate. Now, in this method, we take the tangent at that point. This is the point x2. Now, let us see the corresponding ordinate of x2. That is x2 comma f of x2. Again, let us take the tangent at this point. This is the corresponding point x3. Notice how as we are taking the tangents, the abscissae are coming much more nearer to the root. Doing this iteratively, x3 comma f of x3, and again taking the tangent, we find that it's going much more closer and closer to the root. This is how Newton located the roots, real roots of this function. Let us see a further mathematical explanation. Notice that this is delta x. So how do we calculate delta x? Delta x would be equal to, tan theta would be equal to f of x1 by delta x, considering this is theta. Now, tan theta is nothing but the slope of the function. Therefore, f prime of x1 would be equal to f of x1 by delta x. Calculating delta x, we get f of x1 by f prime of x1. Therefore, we notice that x2 is equal to x1 minus delta x. Thereby, we get x2 would be equal to x1 minus f of x1 by f prime of x1. Okay. Let's find out x3. x3 would be x2 minus delta x, which would be, from the previous result, x2 minus f of x2 by f prime of x2. So on and so forth. We do it till we find the nearest abscissa to the root. Now x5 would be x4 minus f of x4 by f prime of x4. Notice how we are iteratively proceeding to the root. This is the Newton-Raphson method. Since this is an iterative mapping from f of x2 to x, this is similar to the contraction mapping theorem.
As we saw in the video, it is an iterative map from iterative map from x to f of x. And by the contraction mapping theorem, clearly there can only be one fixed point. Now, the root is at x, and this is also the limit of this mapping. Therefore, from the contraction mapping theorem, t of x is equal to x star. And therefore, we get the root by iteratively proceeding from x1 to x2 to x3 to x4 to x4 and x5 and so on. Now I've written a simple program in C, and let us see this application. Now, this is the simple code I've written in C. Let us take the function x cubed minus 8. Now we know from normal maths that the roots of x cubed minus 8 are 2. Now, let us see from the Newton-Raphson method whether we can arrive at that. Alright, so let us take the arbitrary x naught to be 3, the allowed error to be 0.0001, and let us take the maximum iterations to be 6. Using the function, we arrive at the root 2. Let us take another example. Let us take a more complicated function. How about a sinusoidal function? Taking the differentiation of the sine function, this cos function. Now, let us compile this program. Let me enter an arbitrary x naught. Let us arrive at the function from x naught equal to 1. The allowed error being 0.0001, and let's take maximum 5 iterations. Voila! We get the root 0, which is suitable. Let us try with another root. Let us try to get the root n pi. Let us compile this program again. Let us take our x naught to be 4, the allowed error to be 0.0001, the maximum iterations to be 6. As we see, the function gives us a root of 3.141, which is approximately pi, which is our desired result. The function is perfectly working. The program, rather, is perfectly working. Let us try for a slightly more complicated function. How about a logarithmic function? X times log base 10 x, and that is slightly complicated. The differentiation the same would be log 10 x plus 0.43429. Let us try to compile this. So in compiling, let us try it out. Let me take the arbitrary x naught to be some 3, the allowed error to be again our usual 0.001. Let's try it for maximum 5 iterations. And we see the root is again arrived at perfectly. So our program is perfect. In fact, Newton-Raphson method works for any real function. Feel free, you can try my program and use any real function. So we have seen the Newton-Raphson method. Thank you.